So, hi everyone. I want to thank you for joining me for my talk today, uncovering malware targeting your web applications, where I'll be talking about real-world malware campaign tracking using big data analytics and machine learning clustering. So I want to give a shout out to the organizers of the event. It's been great so far. I've really enjoyed it, and I know that this is the slot after lunch, so I hope that there's enough that's interesting in here to keep you awake for the next 35 minutes or so. Okay, I want to start by asking a couple of questions, and those are: have you ever wondered how threat actors can leverage your vulnerable web servers to spread malware and achieve their malicious goals through widespread campaigns? Have you ever wondered about the techniques that they use, the vulnerabilities that they exploit, and the samples that they deploy? You might even have wondered how you can detect and expose this activity in your own data sets. Well, over the past year, Imperva Threat Research, which is the team I'm a part of, has been working to to answer some of these questions, and we're going to share some of the frameworks that we've developed and some campaigns that we've uncovered with you in the talk today. So just a bit about me. My name is Daniel Johnston. I'm a security researcher within the threat research group at Imperva. I've been in the team for about 6 years, and my domains of specialty are web application security, bot detection, and malware analysis with threat intelligence. So if anyone has any interest in those domains, I'd be happy to chat to you. I'll be floating about throughout the day. So originally, this research was a collaborative effort between myself and a very talented data scientist within the threat research group that I'm a part of as well. Unfortunately, he couldn't be with me today as he's presenting in Black Hat Asia. So he's in Singapore at the minute. So I'll have to try and muddle through this talk without him. Okay, so the agenda. In the introduction, I'm going to be talking a bit about how threat actors can leverage vulnerable web servers in order to deploy malicious samples and achieve their malicious goals. Then I'm going to be talking about some of the data that we collect at Imperva, how we collect that data, what is the significance of that data, and then what we do with it. Then I'm going to move on, and I'm going to talk about a framework that we developed for automating malware handling. So I'm going to talk about how we identify malicious samples in a large HTTP data set, and then how we handle those samples in an autonomous way. Then I'm going to move on and talk about malware campaign identification using anomaly detection and machine learning clustering. And then finally, I'll talk about some of the campaigns that we've been able to identify using the frameworks that we've developed. Okay, so let's dive into the introduction. So at Imperva, one of the flagship products that we have is our Cloud Web Application Firewall. And the idea behind the Cloud Web Application Firewall, or Cloud WAF, is to mitigate malicious attacks or malicious requests from malicious actors, while simultaneously allowing legitimate requests from legitimate actors to pass through and reach the origin web server. We see around 3 billion malicious requests every day, which we store as events in our threat research data lake. So as you can imagine, that's a vast quantity of data that we can then leverage for threat intelligence purposes. And it's something that we get really very excited about because of all the possibilities that affords us. Obviously, there's a lot of work in order to be able to extract value from a large data set like that. And that's what I'm going to be outlining over the next 25, 30 minutes or so. So I want to take a minute and talk a bit about how threat actors leverage web vulnerabilities for their own malicious purposes and their own malicious goals. So in our work at Imperva, we see many different types of threat actor leveraging many different web vulnerabilities in the pursuit of different objectives to achieve or to attempt to achieve certain goals. And obviously there's a lot of other web vulnerabilities and objectives and goals, but these are just some examples. So for example, a threat actor can use a cross-site scripting vulnerability to steal session cookies or session tokens in order to achieve account takeover to then expose sensitive data and then sell that in some kind of a dark market, as we've seen in previous talks today already. But the chain that we're most interested in is the use of RCE web vulnerabilities in order to deploy malware, in order to achieve goals like extortion through ransomware, deployment of crypto miners to use the resources of vulnerable web servers to mine cryptocurrency and make threat actors some money, or botnet deployment to then launch further volumetric attacks down the line. So I want to draw attention actually for a minute to a report that was released by Verizon Business. It's actually already been mentioned today in I think it was the keynote talk. But in that report, the data breach investigation report, they outline just how important of a target web applications are for threat actors in today's landscape. So in that report, they outline that the top action vectors in data breaches in 2023 to 2024 can be like 40% of those can be attributed to web applications. Furthermore, in the report, they say that for non-error and non-misuse breaches, over 20% can be attributed to the exploitation of vulnerabilities in web applications. So that just gives you a bit of an idea of how big of a target web applications are for threat actors today. Also, in that report, they outline vulnerabilities, web vulnerabilities that have been instrumental in data breaches over the past couple of years. And those include vulnerabilities in Atlassian, MoveIt, ManageEngine, and Sugar CRM, all of which we're very familiar with in our work at Imperva, and we've been working to mitigate them over the past couple of years. Okay, so at this stage, I want to show you a bit of an example of an RC vulnerability exploit that we would see in our day-to-day at Imperva. It's an RC attempt of CV 2024-4577, and some of you might already recognize it as an exploit attempt of the PHP CGI vulnerability that was disclosed early in 2024. So this particular vulnerability allows a threat actor to inject a URL encoded soft hyphen to the query string of the request. And what this allows the attacker to do is to append additional query string parameters, which will then tell the web server to interpret the post body of the request as PHP code and execute it on the server. So in this case, the attacker is invoking PHP system. I hope you can see that okay. In order to then invoke MSHTA to download and run a Microsoft HTML application, which might be JScript or VBScript enabled, which will then allow the attacker to run further arbitrary code on the infected server. And this is a great example, but there's some very clear limitations. From this, we cannot deduce what the threat actor is trying to do because we don't know what the file is that's being downloaded. We therefore don't know what the sample is and what the attacker is trying to achieve. And that leads me on to talk about the limitations that we have in the data that we collect at Imperva. So we have no access to endpoints. We have no visibility over endpoints like other vendors do. And therefore, we only really have visibility over the first 4 links in the cyber kill chain. Again, as something that's been outlined in earlier talks. We don't have any visibility over the installation of malware on an asset, for example. We don't have any visibility over the communication between an infected server and a command and control server. And therefore, we cannot deduce any objectives of the attacker, what they're trying to achieve, etc. Therefore, enrichment is clearly required in order to be able to reveal the intent of malicious actors in our dataset. So that leads me on to talk about the framework that we've developed for automating malware handling. So this is a very high-level diagram of the framework that we've developed. And so let's start from left to right. We obviously at Imperva see many different threat actors leveraging many different web vulnerabilities, and they send that to sites, or they attack sites and services onboarded to the Imperva Cloud WAF. So we store those malicious requests as events in our threat research data lake, and it equates to billions and billions of events. So we apply some fairly sophisticated queries and ETLs to be able to extract the malicious URLs from that large data set. We take those URLs to a sandboxed environment, completely isolated from a production environment. We download them, process them, and hash them and store them in an isolated cloud storage. But for each sample that we analyze, we create a log containing the metadata for each of the samples, which we will then re-import back into the data lake to be able to cross-correlate between web application events and the malicious samples that the attackers are attempting to deliver. Then what we do is we enrich that data from threat intelligence sources such as VirusTotal. So that gives us a very rich picture of what threat actors are trying to achieve through their exploitation attempts. Okay, so just a few words about the downloader within the framework that we developed. So it's obviously completely isolated from our production environment. We don't want to be downloading malicious samples within our production environment and potentially risk our key assets. And it's a Dockerized Python service which serves to download, analyze, compress and store each of the samples, and we store each sample named with the SHA-256 hash, which allows us to then retrieve the sample and perform manual analysis if required in the future. So baked into the downloader, we have something that we call second stage URL detection. And so for many samples that are targeting web servers specifically, they're often textual in nature. So what I mean by that, they're often bash scripts or PowerShell scripts that act as second stage downloaders for second stage binaries. So what we did in order to try and extract the URLs from these textual samples was we used to apply a regular expression to try and parse out each of the URLs and then download them with the downloader. But we soon realized that this isn't a great solution because URLs can be split across several parameters, and therefore a regular expression is not going to really cut it. So what we came up with was LLM second stage URL detection. So for any problem in today's world, what do? You take it and you fire it at an LLM and you hope for the best. So what we did was we take the content of the textual sample and provide it with a prompt to an LLM like ChatGPT. And generally, 99% of the time, it's very successful at being able to parse out that second stage URL, and we can then download it and store it in our isolated cloud storage environment. Okay. So just to summarize the system that we developed for automating the downloading of malware samples. Obviously, at Imperva, we have a large volume of HTTP data that we store in our threat research data lake. Then we extract the malicious URLs using ETLs and queries, and we take those samples and we download them in an isolated environment. We create metadata for each of those samples, and we re-import that into the data lake to be able to cross-correlate between the web application attacks and the malicious samples. Then the final piece is the enrichment from threat intelligence sources, where we enrich from places like VirusTotal, sandboxes, and honeypots in order to get a rich volume of data that we can then apply further processing to and extract value from it. Okay, so in this part of the talk, I want to change gear just a bit. And I'm going to talk in technical terms about some of the frameworks that we've developed to be able to extract data from this large data set that we have. So I will say that this part of the talk was supposed to be given by my colleague Ori, but unfortunately, as he's not able to be with me today, I'll be trying to muddle through without him. So I'm going to be talking about the anomaly detection and the machine learning clustering that we apply to this large volume of HTTP data that we collect. Okay, so here is an example. So I'm going to start with the anomaly detection, and here is an example of an anomaly that we have identified in this large data set that we collect. So what's shown in the chart is an anomaly in the exploitation of a specific CVE by a specific HTTP client. And what you see is a fairly even distribution, or a fairly even pattern over time. until you get to around the 2nd of October in 2024, where you see a massive spike of almost 500%. And essentially what this gives us is an opportunity to drill down into the data and understand why the anomaly occurred in the first place. We get to understand what the threat actor is trying to achieve, who the targets are, and what exactly is going on behind it. So here's a second example of an anomaly that we have identified in our data. It's slightly different to the first one. This is tracking injected domains or injected URLs into malicious HTTP requests over time. And what you can see is, again, a fairly even pattern until you reach the end of August, where we see a massive increase of over 600%. And again, this provides us with the opportunity to deep dive into the data behind it, and then understand what the threat actor is trying to do, who's being targeted, and so on. So these anomalies provide us with the opportunity of firstly identifying malicious patterns, and then being able to understand them more fully. So how is it that we actually are able to generate these anomalies? Well, we have a completely serverless architecture. We have a managed SQL engine, which is Trino, and a managed cloud function to do the collection, the aggregation, and the anomaly detection. We have hundreds of counters with which to monitor the anomalous activity, resulting in over 20 million anomalies at any given time. So how is it that we can do this? Well, this is the data flow for our anomaly detection system. And as I mentioned previously in the talk, our threat research data lake has thousands of tables and terabytes of data. And what we do is we read the data from the source tables into a dedicated counters table. And we perform this operation only once. Why do we do that? It's because it's a very heavy operation that requires a lot of aggregation and a lot of filtering. And therefore, it requires a lot of resources. So we only want to do it one time. But once the data is in the counters table, we use cloud functions to do further aggregation and identify the anomalies, which I'll explain a bit later. But the key thing is that everything is done within the dedicated counters table, and this allows us to query it using our query engine and makes it readily available to our analysts. So how is it then that our researchers can define a counter within this anomaly detection framework? We have a dedicated JSON configuration file called a dataset, which is essentially a list of counters that our researchers can define, where each counter is an SQL statement for getting data. So, for example, we might want to track a client over time, or an exploited CVE over time, or any combination within the data set that we have and the data that we collect at Imperva. So we then group by each key to get the hourly, daily, or weekly count for each counter. So for example, we might define a data set for an exploited CVE where we would have counters for exploited CVE plus HTTP client, or exploited CVE plus injected domain or IP. And we have thousands of these counters that we're tracking at any given time. So how exactly then do we do the anomaly detection? Again, we use a completely serverless architecture, a managed query engine, and managed cloud functions and no servers. And we use SQL and the baked-in features of the Trino query engine to be able to do it. So at this stage, I want to appeal to you to actually take a look at the query engines available to you within your own environments and your own infrastructure, because query engines are very, very rich today, and there's more than likely going to be some functions in there that might help you do exactly the same thing and apply these to your own use cases. Okay, so let's look at an example of how we then do the anomaly detection using SQL. So this example is the identification of anomalies based on the distance from average. And the first thing that we do is to collect the data from our data set. The data is already collected and stored within the counters table. So we can query the data for a specific data set, all of the keys and all of the counters, and hold them in memory for a specified period of time, let's say 90 days. So then we can calculate the statistics. In this case, we calculate the average of the data per counter, plus the standard deviation, and then the last stage is obviously to calculate the anomalies. So for this example, an anomaly is any value that's larger than the standard deviation, or than the average plus 2 times the standard deviation, sorry. And what this means is that for any given counter, we can identify suspicious activity where it's spiked within the defined period of time. So it's important to note that we traverse billions of records, and the data doesn't leave the database. So billions of records in just minutes. It's pretty cost effective and efficient. Okay, so I want to move on to talk about malware clustering. So why are we actually doing malware or clustering of malware injection records to begin with? Well, we see millions of requests every day where attackers are attempting to inject malware using web vulnerabilities. And we can't simply hand these millions of records to our analysts and expect them to evaluate them and analyze them in an efficient and effective manner. They just wouldn't get anything done. They wouldn't be able to prioritize them. So we need some way of providing a summary of the attacks, which can be then handled quickly and effectively. So you can see here how thousands or tens of thousands of records have been clustered into a single record, where we have the start time, the extracted URL, and the count of attacks, plus many other fields that I haven't actually added to this slide, but we can then take that and give them to our analysts. So how do we do this? Again, we're using the serverless stack that we know and love. We're using our managed query engine and managed cloud functions. And in this case, the query engine allows us to group individual attacks or individual records into basically attacks. So we can then calculate the distances between the aggregated attacks and then generate the clusters from that. So in the next slide, I'll show you a bit more about how we do that. But both the grouping and the distance calculations are heavy operations, but we can do it using SQL. So the data doesn't ever leave the database, and we don't need additional processes or servers or services in order to be able to do it. So it's pretty cost effective. So once we have the distances calculated, we save the data into an object store where it's moved to the next step, which is the clustering algorithm. So generally within a few minutes, we have our clusters calculated using this method. So in summary, we take the distances, we load them into memory, we run the clustering algorithm, and then we put the results back into the object store. Once these results are in the object store, we can then again use SQL to group similar clusters into ongoing malware campaigns that we can then provide to our analysts for review. So then, how do we do the distance calculations? Again, we're using SQL for this, so it makes it much more cost effective than the alternative of pulling out data into different systems or services, for example, and using data frames. So let's look at an example of what we're doing. We take the attack data and we calculate the distance between every pair of distinct attacks. And we do this by doing a self-join, allowing us to calculate the distance between every distinct pair of records. So by comparing the record on the left side of the join with the record on the right side of the join, we can use many different features to determine the distance between two attacks. We use this, in this example, we're checking if it's the same HTTP client, and we're also using several functions of the Trino query engine to be able to calculate distances as well. So, for example, we're using Levenshtein distance to calculate the distance between two URL paths, and we're also using cosine similarity in order to calculate the distance between two histograms of target sites, for example. So I should say that during the development of this, it obviously took a lot of tuning and a lot of fine-tuning of both the queries and of the clustering algorithm to be able to get it just right. And of course, we have many other features other than the ones that we're showing here, but this is just broadly how it works. Okay, so I want to move on and talk about some of the real-world campaigns that we've been able to identify using the frameworks that we've developed. Okay, so so obviously I can't go through all of the campaigns that we've identified. So there are a few here that I'm obviously not going to talk about, and I won't be able to go into like very great detail in any of them. So if you want to check out more detail about them, they're obviously published in our Imperva blog, which is available on imperva.com. So the first one I want to start with is that of the sysrv botnet. This is a well-known botnet malware written in Go, and it's spread using various different well-known web vulnerabilities. So what we observed was the exploitation of vulnerabilities in Atlassian Confluence and Apache Struts that were used to deploy this campaign and this malware. So the goal behind the campaign is to deploy the XMRig crypto miner in order to use the resources of an infected web server to mine cryptocurrency and make attackers and threat actors some money. So we were able to use the infrastructure and the services that we created in order to identify new TTPs and new IOCs that weren't previously available in the public domain. We were able to aggregate all of the web application events, the web requests, and the attacks, and also along with the samples, and then be able to analyze it in a very effective and efficient way. And we were also able to identify the use of a Google Sites domain hosting the second stage binary of this attack. So as you can see in the screenshot on the right-hand side, you can see what looks like a generic Google 404 error page actually contains the encoded bytes of the second stage binary. So the second campaign that I want to talk about is that of the gsocket PHP botnet. And this is one that we observed in the second half of 2024. It's a hugely widespread malware campaign targeting tens of thousands of PHP web servers. We observed millions of requests containing a payload attempting to install the gsocket reverse shell, which is a tool which allows attackers to maintain persistence on an infected host even after the original vulnerability or the original backdoor has been patched. A deep dive into the campaign actually revealed a link to the propagation of Indonesian gambling using search engine optimization, probably in response to a government crackdown on online gambling in Indonesia. So again, there's full details of this campaign in our blog, and you'll be able to check that out. So the third campaign that I want to talk about is that of Tell You the Past ransomware, which we observed utilizing the PHP CGI vulnerability that I actually outlined earlier in the talk. So this is a ransomware campaign targeting PHP servers specifically, which isn't something that's sort of typical in today's landscape. But it's deployed via a VBScript-enabled Windows HTML application, and it contained the obfuscated bytes of a .NET binary. So you can see in the screenshot on the right-hand side, the S parameter actually contains the encoded bytes of the .NET binary that we were able to extract and decode and load into dnspy in order to be able to understand what the sample was actually doing. So upon execution, it would enumerate the files on the file system, encrypt files, and then publish a ransom note to the web root of the PHP server. Again, it was quite an interesting one to find because it targeted specifically PHP servers for ransomware deployment. Okay, so the final campaign that I want to talk about is that of that one that we believe we can attribute to APT29. So APT29, also known as Cozy Bear, is a threat group that's associated with the Russian SVR or Foreign Intelligence Service, and they've been associated with many notorious cyber attacks over the past few years, including the SolarWinds supply chain attacks and the mass exploitation of JetBrains TeamCity servers last year. So in March of this year, we observed a very coordinated and very targeted attack against Polish government assets, and A further attack that we observed in November was targeting Ukrainian financial institutions. So the attack involved the exploitation of F5 big IP vulnerability, a vulnerability in a well-known load balancer application, in order to attempt to deploy the Sliver implant. So for those of you who are unfamiliar, Sliver is an open source alternative to Cobalt Strike, developed by Bishop Fox, and it allows for a range of post-exploitation activities on an infected host, such as information gathering and further arbitrary command execution. So how is it that we were able to then attribute this activity to APT29? Well, there's three reasons. Sliver is a known TTP of APT29 according to MITRE and Cybereason, so it makes sense if they used those particular tools in the past, that they'd use it in this campaign as well. Secondly, the C2 that we observed is linked with previous APT29 JetBrains and Team City campaign activity. Again, if the piece of infrastructure was used in the past, in past campaigns attributed to APT29, then if we observed it in this one, it's a good indication that it is that threat actor. And then thirdly, only targets of interest to the Russian state were implicated in this particular campaign. So Ukrainian financial institutions and Polish government websites gives a strong indication that this is a Russian threat actor. Okay, so on to the conclusion and takeaways. So we have three main takeaways I think we can take from this talk. Firstly, automation, big data analytics, and anomaly detection provide excellent tools for threat hunting at scale. And I hope that through what I've talked about in the slides and in this presentation, you can take away some ideas that you'll be able to apply to your own data sets that you have. Secondly, threat actors such as the ones demonstrated are regularly leveraging web vulnerabilities for malware deployment. And this is something that we're seeing day in and day out in our work at Imperva. And it's also something that's backed up by the data breach investigation report that I outlined earlier. And then thirdly, the identification, the correlation and tracking of malware campaigns has great and real community value. And it's something that we're seeing as we're publishing blogs from this infrastructure that we've created, that they're very well received by the public and by the community in general, because it allows then the IOCs and the TTPs that are published in those blogs to be used in other investigations in other organizations. Okay, so that is all that I have for today's talk. I want to thank you for listening, and if anyone has any questions, I'll be floating about here, so please feel free to come and chat to me. Thank you.